Okay, the comparison tests. Direct comparison and limit comparison. They both require you to know the answer ahead of time. So you have to know what series you want to compare with. And the way you'll do that is by using the rule of thumb. I call it the ROT. So to see how a series behaves, you look at the dominant terms in the numerator and the denominator. So for example, this series here, upstairs, it pretty much looks like n squared. Ignore the 2. Downstairs, the dominant term is n to the 5th. Ignore the 4. So this is equal to the sum of 1 over n cubed. So if we wanted to show this converges or diverges, we'd actually be trying to show it converges because it behaves like this series, and this is a p series with p equal 3, and 3 is bigger than 1. So that would converge. The next one, if we were trying to figure out if it converged or diverged, the dominant term upstairs is n. Downstairs, it's the square root of n to the 6th. That's n to the 6th. Square root is 1/2. So that's n over n cubed, which is 1 over n squared. Sum of 1 over n squared. So we would assume that this one converges also because it behaves like the p series 1 over n squared, and p is bigger than 1. Okay, so the direct comparison test. Suppose you have an infinite series, two infinite series with positive terms, and your ANs are less than or equal to your BNs. If the series with the larger terms converges, the BNs are larger, then the series with the smaller terms converges too. And if the series with the smaller terms diverges, then the series that has the larger terms must diverge also. So it makes good logical sense. So let's try using direct comparison. First of all, we need to decide what we think this does. So this looks like, or behaves like, so this is informal, we're not proving anything. We're just saying, well, this looks like n over n cubed, because the highest power in the denominator is n cubed, which is the sum of 1 over n squared, which converges. So we're going to try and show that our series converges. So what we have to do is take the terms and show they're less than terms from a convergent series. So pull out the terms without the summation sign, n over n cubed plus 4 root n. All right, and we want to show that's less than terms from a convergent series. Well, I can ignore the 4 root n because this denominator is bigger than this denominator. So the fraction is smaller. So this is a true statement, but that's 1 over n squared. 1 over n squared are the terms from a convergent series. So the conclusion is this series converges by direct comparison with the sum n equal 1 to infinity of 1 over n squared. Now, I want to point something out. When you make your comparison, you cannot put the summation sign in your comparison. So you cannot write this. On a test, you will get 0 credit for that. 0. There's a few rogue videos out there on YouTube where they use the summation sign in their comparison, and that's completely wrong. And so where do you put the summation on? You put it back on in your conclusion. Okay, let's do another one. What does this look like? This looks like the sum of 1 over n. Just ignore the negative 4. And that is a divergent p series. So we're going to try and show our terms are bigger than terms from a divergent series. So now the inequality has to go like that. If you're trying to show converges, the inequality goes less than. If you're trying to show diverges, the inequality goes greater than. So this denominator is less than this denominator. And that does it because those are terms from a divergent p series. So my conclusion is this guy diverges by direct comparison with the sum n equals 1 to infinity of 1 over n. Let's do one more. This test is limited. I want to warn you, this test is limited because the comparisons you make have to be very basic. If the terms are complicated with a lot in the numerator and a lot in the denominator, then you're going to use the limit comparison test, which we'll talk about in a minute. Use direct comparison to show that ln n over n squared converges. Here are two inequalities that you can use without having to prove anything. You can just state them. First of all, natural log ln n is less than n. Here's a graph. ln n grows much slower than n. This red graph lies way below the green graph. Sometimes, though, that comparison isn't strong enough and you need a stronger one. ln n is less than the square root of n. That's a stronger comparison. And here's an example where the weaker one doesn't work. If I use the weaker comparison, ln n over n squared is less than n over n squared, that's a true statement, but it doesn't help me show that this converges because 1 over n diverges. That's a p-series. So I have to use the stronger inequality. I go ln n over n squared less than square root of n over n squared, which is 1 over n to the 3 halves. And that's a strong enough statement. This converges because this p-series, 1 over n to the 3 halves, has p bigger than 1. So now let's use a more versatile test. Limit comparison. It's kind of got a long statement, but it's not hard to use. Again, you have to know ahead of time whether your series converges or diverges. So you pick a series that you want to compare it with using the rule of thumb. And the series you're going to compare it with is usually a p-series. And then you take the limit as n goes to infinity of the given series, the terms, an, divided by the terms from your series, bn. If L is not 0 and not infinity, then the series that you're given, the ANs, will do whatever the series you compared it with does. Those series converge or diverge together. There are two other statements, which I'm not even going to mention. You can read that. Most of the time, 99% of the time, you're going to be showing L is not 0 and not infinity and using case A. Let's do an example. So let's use a rule of thumb to decide what we think it does. Highest power on the top is n, highest power on the bottom, n cubed. So that looks like 1 over n squared, which converges. We haven't proven anything yet. So usually you're going to be dividing a fraction. These are your ANs. You're dividing by your BNs. These are usually going to be fractions, and so I always skip this step, and you're welcome to skip it too. I jump straight to multiplying an by the reciprocal of the bn. So instead of dividing by 1 over n squared, I multiply by n squared over 1. And this is L, and so that gives me this, which is infinity over infinity. So L is limit n goes to infinity. I'm going to divide top and bottom by n cubed. By n cubed, that's the highest power in the denominator. So upstairs I get 3 plus 4n squared over n cubed over 1 minus 4n over n cubed plus 5 over n cubed. Let's simplify. I could have done that simplification in my head. This is 3 plus 4 over n divided by 1 minus 4 over n squared plus 5 over n cubed. So that's 3 plus 0 over 1 minus 0 plus 0, which is 3. The significance of 3, it has no significance other than 3 is not 0 and it's not infinity. That's all I care about. And so what I can say now is that this series, the original one, does exactly what the series I compared it with does. The series I compared it with converges. So my series converges by limit comparison, LC, with the sum n equal 1 to infinity of 1 over n squared and L equal to 3. You always want to state what L is if you're using limit comparison. Let's do a couple more. This looks like you're always going to start by trying to decide what's going on. So this looks like sum. The highest power in the denominator is just n, because square root of n is a smaller power. So that looks like 1 over n, which diverges. This is my bn in the test. So I'm going to take L, which is the limit, as n goes to infinity of the ANs divided by the bn's, but instead of dividing by 1 over n, I'm going to multiply by n over 1. That's the limit as n goes to infinity of n over n to the 1/2 plus n. Now that's infinity over infinity. So I'm going to divide top and bottom by the highest power in the denominator, which is n. So the limit as n goes to infinity, n over n is 1. N to the 1/2 divided by n is 1 over n to the 1/2, and n over n is 1. So just so you didn't miss that, I'll do my scrap paper over here. I took n to the 1/2 and I divided by n, subtract the exponents, that's n to the negative 1/2, which is 1 over n to the 1/2. Okay, now I can take the limit. I get 1 over 0 plus 1, which is 1. The only significance of 1 is that it's not 0 and it's not infinity. So my series must diverge because the series I compared it with diverges. So this guy diverges by limit comparison with the sum n equals 1 to infinity of 1 over n and L equal to 1. Okay, I'm going to do one more because it's got a square root in it, and I want to show you two different ways to take the limit. It's just the algebra that might trip you up there. So first of all, this looks like the sum of 1 over n times the square root of n squared. N squared to the 1/2, which is n, right? Because you multiply the exponents. So n times n is n squared, which converges. We'll just use C for converges. So that's the series I'm going to compare with in the limit comparison. So L is the limit as n goes to infinity of the ANs, which are 4 over n times the square root of n squared minus 8 times the reciprocal of the BNs. Okay, so if I simplify this, cancel one of the n's, that's the limit as n goes to infinity of 4n over the square root of n squared minus 8. Okay, so here's method 1 for finding this limit. So method 1, this is equal to the limit as n goes to infinity. I'm going to divide by n over n, but downstairs I'm going to write n as the square root of n squared so that I can get that n squared into the square root part. So that's the limit as n goes to infinity, 4 over, now this is one big square root, divide each of these terms by n squared. So n squared over n squared is 1, and then I have 8 over n squared. Now I can take the limit, that's 4 over the square root of 1 minus 0, so I get 4. Here's the alternate way to take this limit. So remember, our limit is n goes to infinity, 4n over square root of n squared minus 8. Limit n goes to infinity. Think of 4n as the square root of 16n squared. And that way you can combine everything under one big hat. Limit as n goes to infinity, one big square root, 16n squared over n squared minus 8. And now divide top and bottom inside the square root by n squared. So that's limit. Okay, there's no short way no matter what you do. I hope you're getting that feeling because there's no quick way to do this. I'm giving you two options, but neither one is going to be instant. So this is square root of, divide 16n squared by n squared and you get 16. Divide n squared by n squared, you get 1. And divide 8 by n squared, you get 8 over n squared. Okay, now take the limit. You get the square root of 16 over 1 minus 0. Square root of 16 is 4. So same answer, just a different method. You use whatever one you like the best. And so what's our conclusion? Well, our conclusion is our series converges because we compared it with a convergent P series, and L was 4. Okay, and that is the end of this section.